This is Michael Wunsch. I'm the plant pathologist at the Carrington Research Extension Center, and I am re-recording the presentation on soybean white mold management that I gave at the online Getting It Right in Soybean Production meeting on December 19th. There were some concerns about audio quality, so I'm re-recording now. Now this recording will be a little bit longer. I've included a bit more data that I did not have time to cover in the original presentation, and I will also explain things a little bit more clearly because I have a bit more time. Very first, I'd like to give sincere thanks to my staff. I have very dedicated, hardworking, full-time staff who assist in this effort, and their dedication makes this all possible. They all work just like me, very long hours in the field throughout the growing season, and in the case of Jesse and Sue-Ann, they do so with no overtime pay. So they are very dedicated, and their efforts are sincerely appreciated. So from left to right, that's Aaron Faust, a research technician, Sue-Ann Callis, a research specialist who's worked with me now for 8 years. Jesse Hafner on the very right side of that picture on the top is a research specialist who started actually as a high school student with me 12 years ago. So very long-term dedicated staff, and I'm grateful for them. Also, gratitude goes to the staff in Oaks. Almost all of our white mold research is conducted at Carrington and Oaks. And Oaks is an irrigated sand, very typical of the irrigated soybean production in North Dakota. And their efforts are sincerely appreciated. This research would not be possible without your checkoff dollars. The Soybean Council has been very generous in supporting this research over the years and has been instrumental. All the data that you're going to be seeing here and all the recommendations are made possible only through your checkoff dollars. I would also extend gratitude to the private companies who do fungicide efficacy testing with us. Their funding support through doing this contract testing research gives us the flexibility of funding to be able to cover all those unexpected expenditures. So when we have a well, a pump on a well that needs to be replaced, or a VFD that needs to be replaced on a well, or having an unexpected repair that comes up on a tractor or a sprayer, this is what we use. These are the funds that we use to cover those expenses. These are also the funds that we use to purchase new equipment, such as plot combines and things like that. I'd also mention that I would express my gratitude to the dry bean growers. You'll see some dry bean data in this presentation, even though it's a soybean presentation, because there are certain circumstances where our results from dry beans illuminate what we would expect to find in soybeans. Okay, and so again, that's checkoff-driven research funded through the North Harvest Bean Growers Association. In this case, with support from the North Dakota Crop Protection Product Harmonization and Registration Board, which funds pesticide utilization research on minor crops, and also from the USDA Specialty Crop Block Grant Program administered by the North Dakota Department of Agriculture. So the very first subject that we're going to cover is what you should be thinking about before planting when you are worried about white mold in soybeans. So the very first of these subjects is, does it work to plant into winter rye? There's a lot of discussion, especially in other regions of the country, that planting your soybeans into winter rye is an effective management tool to reduce white mold pressure. We've tested this not on soybeans, but on dry edible beans. and the results from dye-edible beans, I believe, and I think you'll also agree, are highly informative in terms of what you would expect on soybeans. So what we have found on dry-edible beans is that planting into a winter rye cover crop only produces white mold if the rye has significant biomass when the susceptible crop, in this case a soybean, but our data are from dry beans, is planted. Okay, and so in dry beans we only saw a reduction in white mold when the rye was headed out when we planted the dry beans. So when we terminated the winter rye, typically 2 weeks before planting, when the winter rye was still at very early stem elongation stage and the biomass was very limited, we did not see any reduction in white mold in the subsequent dry bean crop. We only saw it when we planted into standing rye that was at heading, and then terminated the rye 0 to 3 days after planting. Okay, and so what's going on here is in our apothecia assessments and assessments of the little mushroom-like structures that produce the sclerotinia spores, when you had significant biomass from that winter rye crop, it shifted the spore production of the sclerotinia fungus earlier in the growing season, such that a lot of those spores were released before the dry bean crop entered bloom. Okay, and that only happened if you had a lot of biomass from that winter rye crop. Okay, and so the big problem that we run into, especially in our climate, is that planting into a fully headed winter rye crop and then terminating 0 to 3 days afterwards, that can reduce yield potential. That winter rye draws a lot of moisture out of the soil, especially as it's preparing to enter anthesis, and so soil moisture levels are much lower, and this can reduce yield potential. And basically, what we found is that planting into fully headed winter rye, yeah, it did reduce white mold, but also reduce yield potential. And in the end, although we had less white mold, we didn't increase yields. You might find something different in a region with a longer growing season or a place that's wetter, but in an area with a longer growing season, you could presumably terminate your rye at heading and then wait 7 to 10 days until you get some good rains to recharge the soil with moisture before you plant. Here are the results from kidney beans. What you'll see if you look over the top is that in every study we saw either a numerical or a statistical reduction in white mold with planting into that fully headed rye and terminating 0 to 3 days later. And in that combined analysis, you'll see that statistical reduction. You do not see a reduction when that rye was terminated at an earlier vegetative stage. Typically it was done about 2 weeks before planting, but you can see, depending on the study, it was 8 to 25 days. Okay, and then look at the yield data. On average, it's a complete wash. I mean, like no difference in yield across those treatments. So what this means is that the yield gain that you achieved by reducing white mold just compensated for the yield loss associated with the moisture removal from that headed out rye from the soil. Okay, and so this worked okay in this situation because we had significant white mold pressure. But let's say it was a year where you hardly had any white mold. All that's going to happen is you're going to have a lower yield from the headed out rye. Okay, and so I guess that's a cautionary note, right? On pinto beans, we saw a very similar response, although it wasn't quite as consistent. Over the top, you can see across these 4 studies, you can see in 2 of the 4 studies, we saw a statistically significant reduction in white mold when we planted the pinto beans into headed out rye. Okay, and the other 2 studies there was not a reduction, okay, or at least not a statistically significant reduction. Okay, if you look down over at the combined analysis, you'll see exactly what we found in the kidney beans, that reduction in white mold did not confer a net yield increase. Okay, and so same problem. Okay, same problem with that headed out rye is drawing too much moisture out of the soil. Okay, the next consideration that you need to be thinking about before you plant is row spacing. And what I'm going to be presenting here are results from very comprehensive studies conducted at 4 locations across North Dakota in a wide range of soybean varieties differing in architecture, bushiness, and height, all the way from a 00 maturity bean up in Langdon down to soybeans approaching, 0.9 maturity, I think was the longest that we did, okay, but approaching 1.0. Down in Carrington and Oaks. Okay, and our results, while they might seem surprising because they go against the conventional dogma, are actually highly consistent with what researchers have found elsewhere. It's highly consistent with what Craig Grau's group found in Wisconsin in the 1980s, and what researchers up in Manitoba found a decade ago. The difference is that the data that we've generated here in North Dakota are much broader in scope, and the data set is much deeper, and so it's much easier to draw very definitive conclusions. So what we found is that if white mold incidence is kept below 50%, okay, that's half of the plants with white mold at the end of the season, okay? Soybean yields are optimized with intermediate row spacing, okay? And our testing was done with 21 to 22.5-inch rows. I'm sure you'd find something very similar with 20-inch rows, okay? Surprisingly, the narrow rows, 14 or 15-inch rows, perform similarly. To keep this talk of more moderate length, I'm only going to talk about the intermediate rows because those were better under white mold than the narrow rows. Okay, and if you're worried about sclerosis contamination in the grain, we will cover that. The difference in sclerosis contamination of the grain, i.e. those black structures of the white mold fungus that you'll find in the harvested grain, if you're worried about that, the difference in the contamination of the grain with those structures was negligible between the 30-inch rows and those intermediate rows, as long as the incidence was below about 30 to 35% at the end of the season. All right, so these are the combined results across all the varieties we tested at different locations over the 4 years we conducted this research. And so you'll see that these are combined results over a large number of varieties. Under that very low disease pressure category on the very left, 0 to 15% incidence, you'll see that's the combined results across 26 varieties. You go across and you'll see, again, a large number of data points contributed to these averages. Okay, but what I want to point out to you is that consistently we saw less white mold in the wide rows. Okay, and this is exactly what everyone knows. You get less white mold in wide rows. Okay. Okay, under the very low disease pressure and into moderate disease pressure, up to 30% incidence of white mold at the end of the season, what you saw though is that yes, you minimized your white mold, but you did not maximize your yields. All right, and you maximize your yields with that intermediate row spacing. There was not statistical separation relative to the 14 or 15-inch rows, but I mean numerically it was better. Okay, and so what you need to be thinking about here is that the conditions that favor white mold are not moisture limiting conditions. Obviously, white mold is a disease you get when there's a lot of moisture as those soybeans are entering bloom. Okay, when there's abundant soil moisture, typically, anytime you have significant white mold pressure, you have plenty of moisture as those soybeans are in bloom, which is the susceptible window for white mold. And so what happens is that obviously the soybeans are putting on abundant vegetative growth as they're entering bloom, which is why you see that canopy closing at, R1 into R2, even into R3 if you're in wide rows. And so what happens is that when moisture isn't limiting, there's a real yield penalty to having exposed ground where the sunlight is not being captured and converted into blossoms and pods. Okay, and so the yield penalty to seeding to wide rows is particularly high when moisture isn't limiting. Okay, and so under the conditions favorable for white mold, you have a significant yield penalty to planting to wide rows. Okay, so what's going on here is that, yeah, you've improved your white mold management. The improvement in white mold management in those wide rows is not enough to overcome the yield loss that you got by planting into wide rows when moisture wasn't limiting as those soybeans were going into bloom. Okay, so as you get to higher levels of white mold, 30 to 60% incidence, you'll see that again you're minimizing your white mold quite sharply. Now, it's moderate, and it's not moderate anymore. Now you have a sharp reduction of white mold in those wide rows, but you notice the yields, it's basically a wash. Okay, so the yield gain you get by reducing your white mold is really equaled out by the yield loss associated with not capturing that additional sunlight as the soybeans are in the earlier stages of bloom. And as you get to extreme levels of white mold, 60 to 90% incidence, you'll see then finally towards the end, you're starting to get a yield gain with those wide rows. But I mean, this is wipeout territory. I mean, this is some awful white mold. All right, so here's another way to look at those data. Okay, so every one of these dots is the result from one variety evaluated in a replicated pattern in these different row spacings across one of these 4 study locations across one of the 4 years. Okay, and what this is showing is the increase in white mold that you observed in the intermediate rows versus the wide rows relative to the disease pressure, the level of disease in the study. Okay, and what you can see is that as disease pressure goes up, your increase in white mold associated with planting intermediate rows goes up. And this is exactly what we just showed. Intermediate rows, you get more white mold than in wide rows, period. But here's the yield relationship. Okay, so under low to moderate disease pressure, you're consistently getting higher yields in those intermediate rows, consistently, okay, with very rare exception. And it's once you hit about 50-55% incidence that you start seeing a fair number of cases where you actually get higher yields in the wide rows. And on average, that trend line doesn't cross until about 65, 66, 67% incidence. Okay, but basically, if you can keep your white mold incidence below 50% end of the season, you're maximizing your yields with those intermediate rows. And again, and then here are the data for the sclerotic examination of the grain. You can see that the number of data points is a little more limited here because we didn't assess this every single time. This is very labor-intensive work to assess this. But what you can see is that if you could keep your white mold incidence below about 35%, then the amount of the percent sclerotic contamination of the grain was very similar between those intermediate rows and the wide rows. Okay, and as the disease pressure went up, then it started to widen. Okay, so basically your market grade is going to be unaffected by your row spacing if you can keep your white mold below about 35%. All right, the next consideration before planting is seeding rate. Okay, we conducted this seeding rate research with across all 4 row spacings. This was done in the same studies as the row spacing research. Okay, and what I just showed you with the row spacing research were combined results across 3 different seeding rates: 132, 165, and 198,000 viable seeds an acre. Okay, the results were consistent by seeding rate. The row spacing results were the same irrespective of the seeding rate. And now we're going to look at the impact of seeding rate. And now this is across all 4 row spacings because the results were consistent. Okay, it didn't matter your row spacing. And basically what we found across these 3 seeding rates, there was no impact of seeding rate on white mold. Unfortunately, I don't know how informative this really is. Okay, I conducted this research with my team, early on, and subsequent to completing this research, my conversations with stakeholders have indicated that those producers who use seeding rate as a tool for white mold are typically planting all the way down at about 100,000 viable seeds an acre, and we didn't test that. So how well that works, I have no idea. We just haven't tested it. It's a hole in our data. Okay, but here are the results for the seeding rates that we did test. You can see, irrespective of the disease pressure, there was no impact of seeding rate on white mold. There was, however, an impact of seeding rate on yield, especially at the lower levels of white mold pressure. Okay, where we saw statistical separation with the higher seeding rates in terms of yield. Okay, and whether or not that pencils out in terms of profitability is something, every person needs to calculate and will depend on the seed costs. Sclerosis contamination, the grain data corresponds to the white mold data, like you'd imagine. There's just no response, no impact of seeding rate on sclerosis contamination on the grain within the seeding rate ranges that we tested. So basically what we've learned here is that in order to maximize your yields when you're concerned about white mold, you really want to keep your white mold incidence below 50%, and if you want to maximize quality, you want to keep it below 35%. And frankly, you want to stay below those levels anyhow because of the yield impact that white mold has as you're getting into that territory. So the tool that we have here is really fungicides. Okay, yes, varieties differ in their susceptibility to white mold, but with the turnover in varieties that the companies have, it's really hard to do to generate independent data on the efficacy of individual varieties. Okay, and so yes, if you're worried about white mold, go select a variety that has a better white mold rating. That's going to help you. But beyond that, your tool is fungicides. And so what I'd like to cover is our fungicide optimization research. Now, this research has been highly productive and has showed that you can make really strong gains by optimizing fungicide application timing and droplet size and application frequency. Okay, and a lot of what we have found goes against common practice, and frankly, it goes against the long-standing recommendations that you found from everybody. Okay, the private companies, from university people, and I want to tell you and warn you, those recommendations are, for the most part, have been developed on the basis of very limited data. They make a lot of sense based on what we know about soybean growth and development and when soybeans are susceptible to white mold, but they aren't based on data. And once we went out and tested these concepts, we found that the traditional recommendations were usually not right. And once you thought about the results relative to what we know about white mold, about the Sclerotinia fungus and soybeans, it all makes sense as well, and it actually makes a lot more sense. And so I'm going to walk through each one of these subjects, starting first with fungicide application timing. All right, before we get into the data, let's talk a little bit about how fungicides work. Okay, and because this is something you need to understand in order to understand optimal fungicide application timing. First, fungicides must always be applied prior to pathogen infection. Now, this is different than disease symptoms. Okay? Some, but not all modern fungicides exhibit some degree of curative activity. Okay, this is the so-called kickback. But this curative activity is limited to controlling a microscopic infection, usually within 24 hours of a spore penetrating the leaf or the stem. Okay, so this is a level of infection that you would detect only if you took microscopic sections of your plant tissue and stained them with a differential stain that would stain, say, fungi versus plant material, and looked at very thin slices under the microscope. It takes days, even weeks, before that microscopic infection manifests itself as disease, visible disease. And a lot of our modern fungicides don't even do that. They just prevent the penetration of the germinating spore into the plant. Okay, so you've got to get this fungicide on before pathogen infection, or if you have a fungicide that has some kickback, within usually 24 hours of microscopic level pathogen infection that you'll never see with your eyes. Okay, so all applications must be risk-based, based on when you know the crop is susceptible and when you believe the conditions favor the disease. Okay, you can use like the Sporecaster app, or just your knowledge of the pathogen and the susceptibility of the crop to guide your decisions. But the fungicide must go on before pathogen infection. And we're talking microscopic level of infection, okay, or within 24 hours of infection if you have some kickback. But even then, the fungicide works better before infection, okay? And this must be risk-based. Okay, if you wait until disease symptoms, it's over. I mean, it's over, especially on white mold, where the lag between pathogen infection and the appearance of disease symptoms can be quite long. All right, the second concept that you have to understand, and that most people do not think about, is that new growth is not protected by the fungicide. Okay, you really have to understand this, because what this is telling you is that only the biomass that exists at the time that you apply the fungicide is protected. You know, it might be that a little tiny bit of the fungicide is brought forward with new growth from whatever bud or something was treated with the fungicide, but the problem is you have to realize is that the concentration of that fungicide is going to be so small that it's not going to provide control. All right, and so this is a real problem, because as we discussed earlier, when soybeans are in bloom, especially the early stages of bloom, they're putting on lots of biomass. And you know this because you can see, especially when you're in those wider rows, how that canopy is closing on you. Or irrespective of the row space, you can see how the soybeans are getting taller. I mean, there's a big bump in soybean height between R2 and R3. And especially between R1 and R3. And this is, I mean, R2 full bloom, this is like maximum susceptibility to white mold. And so new growth is not protected. So what this means is that if you apply your fungicide too late after pathogen infection, it's not going to work very well. Not going to work at all, okay? Unless you get some more infections after you apply. All right, and but if you have new growth occurring, which you do after the fungicide is applied, all that new growth is unprotected. So what this means is that it's really tricky. Okay, it's not as simple as just getting on before the pathogen infects. There's also penalty applying too early. Okay, and this is why we don't apply, for instance, our white mold fungicides at late vegetative growth. Okay, because all that new growth is unprotected. Okay. All right, so here's a visual example of new growth not being protected by the fungicide. This is from field peas. This is a disease called powdery mildew, which you may very well be aware of in other crops, or maybe your garden on various crops. And basically we applied the fungicide here at early bloom, and subsequent to that, the peas put on additional growth above that on the very tip of the plant, putting on additional leaves and stem leaves and blossoms and pods. And what you can see here is that as we were approaching full pod fill, the bottom of the canopy is fully protected. Okay, it's whistle clean, which is the growth that was present, the biomass that was present when we applied the fungicide, and all that new growth is white from the powdery mildew. Okay, so that illustrates my concept. All right, so what did we find in our fungicide timing research? What we found is that when conditions favor white mold as soybeans enter bloom, fungicides should be applied as soon as 100% of the plants reach the R2 growth stage, unless the canopy closes earlier. Okay, I mean, if the canopy is already closed at mid-late R1, so this would be 60 to 85% of plants in bloom when we did our testing. Okay, you should apply the fungicide then, if conditions are highly favorable for white mold. I mean, if they're not favorable for white mold, you need to wait. Okay, and we found that if the canopy closed at early R2, so this would be fewer than 100% of plants at R2, then you should apply it then, if conditions are highly favorable for white mold. Okay, and as always, if conditions do not favor white mold, whether it's R1 or R2, or even R3, I mean, you wait until conditions are favorable for white mold to make that fungicide targeting white mold. Okay, and but we did our research, basically worst case scenario, where we used overhead irrigation to ensure that at least moisture conditions were favorable for white mold. We can obviously not control temperature. Okay, and so here are the results from our original research conducted these are data from 2015 and 2016, depending on the data slide, Carrington and Oaks. And this is the combined results across 4 studies, and these were studies in which the canopy closed at late R1, which would be 60 to 85% of plants in bloom. Okay, I indicate R1, but usually if the stand is not completely even, a few of those plants will already be at R2. And what you can see here is that we sometimes optimized our the performance of the fungicide by applying at R1 when the canopy was closed when. If you look at the scatter plot, you can see that in 2 of the 4 studies, we optimized with white mold management with an R1 application. But in 2 of the 4 studies, we actually optimized by waiting until 100% R2, even though the canopy was closed at R1. And so basically this goes back to how favorable are the conditions for white mold. If the conditions are highly favorable for white mold and the canopy is closed at R1, what these results indicate is that you should apply at R1. Okay, in this case, late R1. Okay, but if conditions are not highly favorable for white mold, you're better off waiting, okay, until R2. All right, and here are the results from 2 studies in which the canopy closed at early R2. And what you can see is that in this case, in both of these studies, we optimized by applying at early R2 concurrent with canopy closure rather than waiting till 100% R2. And there's only a 2 to 3 day difference, even 1 to 3 day difference in this timing. Okay, very small. Okay, so again, this goes back to that idea that you have to get on the fungicide before pathogen infection. Okay, and so in the rest of the studies from these, this is a combined results across 6 studies. These are studies where the canopy did not close until 100% R2 or even R3. Okay, in these studies, we consistently optimized our the performance of our fungicide by waiting until 100% R2. Okay, so until 100% of the plants were R2. And what you can see here is actually what you are achieving here is a 50% increase in the yield response to the fungicide, just by getting your timing right. And so again, the reason why that R1 application in this situation is not optimal is because that canopy is open, which allows the drying of the canopy and reduces the number of infections you get. Okay, and it might very well be that we got a couple infections at early R2 or very late R1, but the price of protecting against those infections was carried by the fact that the new growth wasn't protected. And you were better off waiting until 100% of the canopy was at R2, okay, to make that application, because that way you also protected all that new growth, and you hardly had any infections anyhow before then. Because with the canopy still being open, you had a lot of drying of the canopy between moisture events. And we irrigated these studies during early bloom here, and so we made it favorable for white mold, okay? So anyhow, one of the questions I always get about this research is, this was early research that we did before we did our droplet size research, and I'll cover the droplet size later. And I always get the question, well, how would results differ if you optimize your droplet size relative to canopy closure? So we looked at this in this last year, in 2023. Unfortunately, this was hand applied, just like these other ones. Nowadays, I'm trying to move our fungicide research into tractor applied, because it's just more precise. It's more expensive for us to run, but it's more precise. But the hand boom is good. I mean, you know, I calibrate my walking pace, and I'm the one making these applications, okay? At least in Carrington, and we calibrate our walking pace, and we're careful, okay? But obviously, you get a even higher level of precision with the tractor. But anyhow, I did this year in Carrington, and this was a 12 replicate study, okay? So we randomized the treatments 12 times. And this is the average across those 12 replicates. So this is extremely rigorous, okay? And what you'll see right away is that canopy was basically closed already at late R1. Okay, and this goes back to my concept here. It was 85% of plants in bloom. In this case, our soil moisture was not the best when we planted the soybeans, and so the soybean emergence was a little variable, which meant that as they entered bloom, they didn't enter bloom evenly. Okay, and so at 85% of plants with an open blossom, already 35% of the plants were at R2. Okay, so that was our late R1 timing. Okay, and you can see at that late R1 timing, we are already at 98.5% canopy closure. Now, what I want to explain to you is that was July 12th. I started overhead irrigation on June 30th, when we had, I think it was like 1% of plants at R1. Okay, and I kept up that over irrigation as needed to keep that top inch of the soil moist and wet. From, frankly, the top half inch of the soil, from June 30th on until the end of R4, okay? And so, and the previous crop here was sunflowers, and it wasn't just any old sunflowers. These were sunflowers that we grew as a sclerotinia head rot management study, and in this case, none of the treatments worked. And so the head rot severity was outrageous, and we had tons and tons of the sclerotia, the resting structures of the sclerotinia fungus on this ground. So you had tons of sclerotia, okay, and you had moisture already for almost 2 weeks straight before the first fungicide application. And this is highly favorable for tons and tons of the little mushroom-like apothecia present underneath the canopy. And this was unfunded research. I didn't assess apothecia, but this is as high risk as you can get. Okay, and then between every single one of these fungicide timings, I applied overhead irrigation with these micro sprinklers that emit a very low volume of water at any given time. But basically what I did was I applied them in such a way to keep the canopy wet for 24 hours straight between every fungicide application timing. You're only going to see this if you get like drizzly wet weather. I mean, or basically it's the only situation you're going to get this. Okay, this is worst case scenario. And look at what you see here. This just blew my mind. So coarse droplets would have been recommended relative to the canopy closure at every one of these timings. Okay, and what you see here is that the fine versus coarse droplets had no impact on the optimal fungicide application timing, but the coarse droplets always gave you better yields. Okay, because again, our canopy was closed. You needed the coarse droplets to get inside that canopy. All right, and so, but what do you see here? We optimized at 100% R2, even though the canopy was closed at R1, and even though the deck was stacked in favor of white mold. So this, of course, goes against the dogma, but it's very consistent with what we found earlier. Okay, and so, but I need to give you now a caveat. All of our fungicide timing research was conducted with a single fungicide application. Now, irrigated producers will often make 2 applications, okay, or folks in higher risk regions for white mold. Okay, and it's very common when you're worried about white mold that you make 2 applications of fungicide targeting white mold in soybeans. Now, our fungicide timing research was done with a single application. Now, this is where I go back to dry beans because we haven't done the work on soybeans. Okay, when making 2 sequential fungicide applications targeting white mold, that first application probably needs to go on 2 to 3 days earlier. Okay, and this is research that we conducted on dry beans, where we actually tested this. Here you have research conducted on pinto beans. This is a combined analysis across 3 studies. On the left side, you see results for a single fungicide application, right side for 2 sequential applications. In this case, this is Topsin or generic followed by Endura. Okay, and what you can see is that the optimal application timing when you're making 2 sequential applications was 10 to 20% of the plants with initial pin-shaped pods. Okay, so this is 10 to 20% of the plants with dead blossoms. Okay, but if you're only doing a single application, you need to wait until 60 to 80% of the plants had dead blossoms. Okay, and so you can see that that's a delay if you're only doing 1 application. So what's going on here is that you are when you're only making a single application, it was better to sacrifice a few early infections in exchange for protecting that additional new growth and extending protection of the canopy of the fungicide into a later period of the growing season when the crop was at maximum susceptibility of white mold. So you're better off sacrificing a few early infections to extend your window of protection, okay, when you're only doing a single application. But if you're doing 2 apps, well, that second app is going to top off, okay, and protect some of that new growth, okay, and so then you want to go on just a little bit earlier, okay, and the difference between those 2 timings was 2 to 3 days, okay. On black beans, we saw the exact same thing. You know, we did this testing on navies, blacks, pintos, and kidneys, but I'm giving you the illustrate, and we saw consistent results throughout. But in some cases, a single application was just not enough, and so the results were less informative. Okay, were less obvious, let's put it that way, less dramatic. And so I'm giving you the examples from those cases where the results are most clearly illustrated. But we saw the same shift consistently. Okay, and here you go again. You notice when you did 2 sequential applications, your optimal application timing was a little bit earlier. In this case, just 2 to 3 days difference, okay, than if you're doing a single application. So what does this mean for soybeans? It means that if, you know, basically our recommendation on soybeans, if you're making a single fungicide application, like I said initially, is that you apply at 100% of plants with as soon as 100% of plants reach R2 growth stage, unless the canopy closes earlier, when conditions favor white mold, okay? And, but if you're doing 2 sequential applications, you probably want to be making that first application a little bit earlier. I would guess it's probably going to run in the range of 40 to 80% of plants at R2, okay? 100% of plants in bloom, 40 to 80% of plants at R2, but that's just a guess based on our dry bean research, okay? All right, so the next subject is optimizing fungicide droplet size. And this is another area where you can make really big gains on the performance of your fungicides. And again, it goes just like the timing research, it goes against the standard recommendation and the dogma, but it makes total sense. All right, first off, we're going to present results from T-jet nozzles. Okay, and what we found with our T-jet nozzles with a single fungicide application applied to soybeans seeded to 14 or 21-inch rows, mostly 21-inch rows, applying fungicides with coarse droplets optimizes white mold management in soybeans when the soybean canopy closure is at or near closure. So in our studies, this was 92 to 100% average canopy closure, and this is average. In some areas of the field, you know, if your average canopy closure, let's say, was 95%, some areas of the field you're going to have 80% canopy closure, and other areas 100% canopy closure. This is the average. Okay. All right, and medium droplets optimize white mold management when the canopy was open, okay, but not wide open, so 80-90% average canopy closure. Okay, and so we did this testing with a tractor-based sprayer. Okay, initially this work was done with the fungicide application pressurized with CO2 like we do with handheld fungicide applications, but eventually we upgraded our sprayer, and the latter testing in the latter years was done with a PTO-driven sprayer. But irrespective, the results are the same. It's just you know, a little easier to run when you have a PTO-driven sprayer. We just had to get a much narrower tank for handle smaller, you know, spray volume, you know, mix-up volumes to do it with a PTO. And any rate, most of the testing was done at 10 miles an hour or 10.5 miles an hour driving speed. Some of the testing was done at 6 miles an hour, and in one study, it was done at 4 miles an hour. Okay, we maintained this constant spray volume of 15 gallons an acre and a constant driving speed across treatments within a study. So within one given study, all the treatments went on at the same driving speed. It was just across studies that we would change driving speed based on how bumpy the ground was. Okay, and if the ground was bumpy, we had to slow down. Okay, and we maintain that constant driving speed across treatments and that constant spray volume by modifying pulse width. Okay, and we have an older version of the capstan system that allows us to manually set the pulse width based on, in this case, we actually measure the spray output with the fungicide in the tank. So that's how we've run these studies. All these studies were conducted with an enormous number of experimental replicates to ensure that we had no bias from hot spots or cold spots in terms of white mold pressure across that field. Okay, and what we found is this: these dots are responses observed in a single study. The bars are average responses across all those studies. So across those studies where the canopy was wide open when we applied at that R2 timing, and again, the canopy was wide open. Okay, but you can see we got a great response from the fungicide, even though the canopy was wide open, because once you hit 100% R2, if conditions favor white mold, it doesn't matter that there's still grounding showing between the rows, okay, because you have enough dead blossoms out there that you're going to get white mold if conditions favor white mold, okay. But what you can see is that when that canopy was wide open, we optimized white mold management with fine droplets, just like the textbook says. Okay, you get great coverage, and when the canopy is wide open like that, you know, the fungicide can penetrate beautifully even with a fine droplet. Okay, and you can see you're doubling your response to the fungicide almost by using those fine droplets versus coarse in that situation. Once you get to 80 to 90% average canopy closure, and this is a visual assessment, okay, just a visual assessment. Nothing fancy, no drones, okay? It's something anyone can do by walking out into their field. All right, then we optimize with medium droplets, okay? And what you're looking at is you're more than doubling your response to your fungicide by getting your droplet size right. Then, once the canopy was 92 to 96% closed when we applied at R2, 100% R2, what you see here is that, again, you're almost doubling the response to your fungicide by getting your droplet size right, but in this case, the optimum droplet size is a coarse droplet. So why? Once the canopy starts to close up, you need the coarse droplet, which has more velocity, to get inside. Okay, yes, you lose some coverage because you no longer have as many droplets, but having tons of coverage with a droplet that doesn't get inside doesn't do you any good, because all the fungicide is captured by the upper leaves where the white mold doesn't develop. Okay, once the canopy starts to close up, you need those coarser droplets that have more velocity to get inside. And so what you can see is you need to apply with as coarse a droplet as is needed to get inside that canopy, and no coarser. Okay, and so and once you get to the canopy basically completely sealed up, so average 98 to 100% canopy closure when we applied at R2, again you can see a very strong response. So applying with coarse droplets, it's not double in this case, but it's more than 50%. So what's the take home here? Is that you can increase the yield response that you get from your fungicide by, on average, somewhere between 65 and 100 plus percent. Okay, just by getting your droplet size right. You're applying at the exact same time. You're applying with the exact same fungicide. You have the same application costs otherwise. All you're doing is getting your droplet size right. If you're lucky, all you have to do is change your pressure, application pressure. If the worst case scenario, you have to change out your nozzles. Okay, and this is an enormous return on investment for just changing out your nozzles. And let me tell you, in order to stay within those extended range XR 110 degree nozzles that we were using across all of our treatments, that coarse droplet treatment was put on at only 30 psi. It's not like we were shooting it in with really high pressure, because we just couldn't do anything else and keep our driving speeds, okay? And so, I mean, this is at, that's only 30 psi. And so, obviously, if you can put in your coarse droplets at 50 psi, well, the more power to you. I would keep it at a maximum of 60 psi, though, because above then, you typically start developing this tail of fines. So if you're shooting it in at 70, 80 psi with pulse width compatible nozzle, you're going to get this tail of fines. Only the air induction tips, which are not pulse width compatible, can be applied at those higher pressures without getting a bad droplet size distribution at high pressure. So here are the results by study. I'm not going to go through this in detail, but what they show is these are the studies where the canopy was nearly fully sealed up. What you'll see as you look across these studies, it was very consistent. Study after study, we optimized with coarse droplets. You can see the yields are at the highest in every one of those studies with the coarse droplets. And here we are with the average canopy closure, 92 to 96%. And what you can see is on the top is that range of canopy closure that we saw. See that blue bar? That shows you the range. This is real world, just like you guys deal with. Some areas were more sealed up than others in the field, okay? And we're talking averages here, okay? And so what you can see is very consistently yields are maximized every single one of these studies with those coarse droplets. And now these are the studies where we had 80 to 90% canopy closure, I guess 80 to 89% really, and average canopy closure. And what you see is every one of these studies, we maximize our yields with medium droplets. Okay, we didn't have statistical separation in any one of those individual studies, but every single one was the same. Okay, and you don't expect statistical separation with these types of small effects when they're this small. Okay, even if you're doing it with 8 to 12 reps like we were doing. Okay, but if you see the exact same thing every single time, and the study is done very rigorously with a large number of replicates, you know that this is real. Okay. And here we are with the fine droplets being optimal and the wide open canopy. And what you'll see is our results were really driven by a single study. In general, we just didn't have enough disease pressure when we had that type of a terrible canopy. Okay, and so at any rate, we certainly don't want that type of canopy, but if we can avoid it, but sometimes we get it, right? All right, so those are results with TJET nozzles. We also did the testing with Wilger nozzles because what we were able to do with Wilger, Wilger manufactures a lineup of nozzles that allows you to change droplet size without changing your output. So with the Wilger nozzles, we were able to run these studies without changing pulse width. Okay, well, we always calibrate our pulse width, but it was always within 1%. Okay, and so essentially these studies are run with, in any given study, you have the exact same spray volume, 15 gallons an acre, the exact same driving speed, and virtually the same pulse width. Okay, again, if it varied at all, it was 1 percentage point. Okay, and again, soybeans were seeded to 14 or 21-inch rows. All right, and what you'll see here is that we saw the exact same response. Our testing was not quite as deep with the Wilger nozzles. We didn't do it for as many years, so the number of varieties tested and the range of canopy closures tested was a little more limited. But you see the exact same relationship. As that canopy closure gets more, you need a coarser droplet to get inside and give you adequate and optimal disease management. Okay, and in this case, though, everything shifted. So when that canopy is open, you actually had to have coarse droplets. Okay, but when the canopy was at or near closure, you needed very coarse droplets. And so one thing you have to realize is that every nozzle manufacturer has its own definition of the droplet size spectrum that would be considered coarse or very coarse or medium, etc. Okay, and so within nozzle manufacturer, within TJET, for instance, our results from the XR nozzles should be consistent across all their nozzles, okay? But that's within TJET. As you go to another nozzle manufacturer, then, you know, they've got their own definition of what that droplet size spectrum is. And so it's very common to see these types of shifts, okay? But what you can see is that the results are exactly the same as with TJET. Again, as your canopy gets denser, you need a coarser droplet to get inside and give you good deposition of the fungicide to the target. Okay, but you only want to get as coarse as you need to get inside, which is why when the canopy is open with these Wilger nozzles, you need to use coarse droplets, not very coarse, because the very coarse droplets, yeah, they would have gotten inside, but you're losing coverage. That was unnecessary to lose. Okay, so here are the results by study. You'll see the exact same thing as with TJET. Results are consistent. You look at those yield response, consistent across studies, every single one of these studies. Same thing again here with the closed canopy. Okay, consistent results across studies. Some of these cases, the yield was low because we really needed a second fungicide application with this type of yield, with this type of disease pressure. But you know, doing a second application was beyond the scope of these studies because then you're dealing with the droplet size you use in the second application. So I want to give you a warning, okay? And this goes back to our dry bean research. All of our fungicide droplet size research was done on soybean seeded to 14 or 21-inch rows. Okay, now these are results from kidney beans. Okay, and this is research results. These are research results from a project that's in progress. We're not done with it yet. Okay, and but these are preliminary results, and they're solid, and they show something that's could be very applicable to soybeans. Kidney beans, typically, what I have found is that typically white bulb management on kidney beans is quite similar to soybeans. It's a bush. It's kind of like kidney beans are a bush. They're not viney like a pinto, okay, or navy, okay. They're a bush. And kidney beans have a pretty broad leaf, sort of like a soybean, except that the leaf is bigger. But still, I mean, what I find is that the kidney beans seem to respond to management strategies quite similar to soybeans. Okay, and look at what we found on the kidney beans. In the first two studies on the left side here, you'll see the row spacing was 14 or 15 inches. Okay, so narrow rows. Okay, and in this case, this is a fungicide application strategy. So what you'll see is that the droplet size is fine followed by fine, fine followed by medium, fine followed by coarse, etc. Okay, and what do you see is that on the very top, you'll see on both of those, you'll see that the canopy was at or near closure at both applications in those narrow rows. And thus, as you would expect, you're optimizing your yields with coarse droplets followed by coarse droplets. Okay, and this is exactly what you'd expect from the soybean. Okay, the canopy is at or near closure, you need coarse droplets. Doesn't matter if it's AP1 or AP2. All right, now, look at the two next studies. Look at the row spacing. Those are 28-inch rows. Okay, so these are wide rows. And the seeding rate was kept the same. Okay, in this case, 90,000 viable seeds an acre, which is on the higher end, but well within the range of what kidney bean producers normally do. So normally a 70 to 90,000, okay, viable seeds an acre is commonly used. But I would assume if you're going to those wide rows, you might drop your seeding rate to the lower range. But in this case, we kept our seeding rate the same. So what happened was, within the row, you had twice as many plants. And what that meant is that the canopy was very dense within the row, even though there was still ground showing between the rows. So look at that. Average canopy closure in that first app was only 81% in those two studies, seeders to the wide rows. But where did we optimize with droplet size? Coarse droplets on that first app, as well as the second app, even though the canopy was, still fairly open on that second app too. Okay, so there was still ground showing between the rows, but the canopy was very dense within the row. So we haven't tested this on soybeans, but if you're seeding your soybeans to 30-inch rows, you probably want to be looking at the density of the canopy within the row when you're choosing the droplet size that you want to be using for your fungicide. Probably. Okay, we just received funding for the Soybean Council to test this on soybeans, and so hopefully we'll have data coming soon, hopefully starting 2024 field season, okay, on soybeans. But these results would suggest that when you're seeded to 30-inch rows, 28 to 30-inch rows, wide rows in soybeans, you probably want to be looking at the density of the canopy within the row, not just whether there's still ground showing between the rows when calibrating your droplet size. Okay. Again, we don't know for sure, but this makes lots of sense. And again, what I've found over and over again is that kidney beans seem to respond to fungicides very similarly to soybeans in terms of white mold management. Okay, the next question is spray volume. Now, the impetus of this study was actually results that have been obtained in other studies. So some researchers in Brazil tested, it was a 10.7 versus 21.4 gallons an acre spray volumes. Obviously, they're using metric units, okay? And when you translate them over into gallons an acre, it gets a little goofy, okay? So 10.7 versus 21.4 gallons an acre. And they found no response to increasing spray volume to 21.4 gallons an acre, okay? This testing, however, was done with a handheld boom with, the walking pace actually changing between those two, spray volumes. And also, obviously, walking pace. Obviously, they were careful and calibrated their walking pace, but still, handheld boom at very, very slow application speeds because you're walking through a dense soybean canopy, right? But they saw a very consistent response in terms of white mold management, irrespective of the fungicide applied or the nozzles utilized. No response to increasing spray volume above 10.7 gallons an acre. We have now conducted this. Through the first 3 years of testing of spray volume on dry beans, we've seen no response to increasing spray volume above 10 gallons an acre for white mold management in pinto or kidney beans. Data from the 2024 season I haven't analyzed yet. We did conduct this study again in 2024. We'll see what we learn. But that was the impetus of this research. And it is research in progress. It's not completed yet. We have one more year of research slated for 2024. But our preliminary results indicate that we have not seen a response to increasing spray volume above 10 gallons an acre. Below 10 gallons an acre, however, we see a penalty when conditions are not very good when spraying conditions are not very good. Okay, so let's walk through those results. All right, this is the response, okay, to the fungicide. So the yield gain conferred by the fungicide. In looking at the difference between a 5-gallon acre spray volume and a 10-gallon acre spray volume, okay, relative to the spray conditions when we applied the fungicide. And what we're using here is a delta T value, which is, and acceptable delta T's are between 2 and 8, okay, and basically what the delta T is it looks at the air temperature and the relative humidity. And if your relative humidity is really high, what happens is that the fine droplets will often hang in the air, especially or they'll drift off target if you got wind. Okay, and when the relative humidity is really low, those fine droplets will often evaporate before they hit the surface. And what you need to realize is that even when you're applying with quote-unquote coarse droplets, that's a droplet size spectrum. You still have some fine droplets in that mix, okay, just a lot fewer. All right, and so you never get away from the fines and the very fines, okay, not completely. And so what we saw here is that at that lower value of delta T, we did have one study where we actually found that a penalty to applying with 5 gallons an acre versus 10 gallons an acre. In the rest of the studies, we did not. Now, that one study was a study conducted early in the morning when the canopy was wet with dew and the relative humidity was still fairly high. It was still within the range of what's considered a preferred delta T value, but it was still, some slightly more marginal spray conditions, okay? Relatively high relative humidity and a canopy wet from dew, okay? And surprisingly, in the rest of the studies, there was no difference in terms of the response to spray volume between 5 and 10 gallons an acre. But obviously, you're rolling the dice a little bit when you're using a spray volume below 10 gallons an acre, because many times you do have to apply to a canopy that has some dew on it, okay? And these were not astronomical levels of relative humidity. I mean, in this case, it was like 70%, 60%, depending on when the application went on. And so it was not that bad. It was just, somewhat elevated relative to how cool it was. All right, and so here you are, the exact same data now, but now we're looking at the disease response. And you'll see that in 2 studies, we saw better disease control with the 10 gallons an acre versus the 5 gallons an acre, okay? And one of these studies, they didn't have yield data, okay, because the yield data were lost due to some harvest problems. But anyway, again, you'll see in both of these cases, these were cases with high relative humidity and a canopy that was wet with dew. But otherwise, there was, the 5 and 10 gallons an acre treatments conferred similar levels of disease control, okay? But again, that 5 gallon acre treatment is a little risky. You have to have really perfect spray conditions for that to work well. So now we're going to compare 10 and 15 gallon acre treatments. You can see irrespective of the delta T, and that's including that one study with that canopy with dew on it, we had no yield gain conferred by going to 15 gallons an acre. Okay, maybe a little bit of one as that delta T value started to get a little bit bigger. Okay, but I mean that's really negligible. Okay, and within the range of noise. All right, and again, that higher delta T is when your relative humidity is getting quite low. Okay, and but really no response. If you average this across all of them, it would be a 0 response. Okay, you can see that visually. Look at those bars. That's the average. The circles are the response given to an individual variety in that study. If you average all that together, it's a 0, like no response to going above 10 gallons an acre. All right, and here's the disease control response for that 10 versus 15 gallons an acre. That one study on the very left side where the delta T value is very low was a study where we lost the yield data. We've discussed the study already. And in this case, we were trying to beat the wind. and we went on to a canopy wet with dew, and the 15-gallon acre treatment went on first when the relative humidity was 99%. And then the 10-gallon acre, when we went on with a 12.5-gallon acre treatment, and then the 10-gallon acre treatment went on about 45 minutes later when the relative humidity dropped down to 91%. Okay, 91% relative humidity is better than 99%. And so basically, the 10 gallons an acre gave you better disease control because your spray conditions were better. Not because 10 gallons an acre was better. It was just the spray conditions were better. Okay, so it goes back to, well, you know, you might be trying to beat wind, but you really shouldn't be applying your fungicide when your delta T is below 1. Okay, all right, and really you shouldn't apply below 2. All right, and so that means that canopy is wet with dew and the relative humidity is quite high. You better wait till relative humidity drops, okay, and into an acceptable range relative to your air temperature to be able to get that fungicide to its target without the droplets just hanging in the air because of how humid it is. The fine droplets, anyhow. All right, so these are the results from individual studies. For anyone who wants to look at this in detail, you can just pause pause the presentation. Basically, you have data here on the growth stage at which the fungicide was applied, the canopy height, and the canopy closure when it was applied by variety, as well as the average results across varieties for that location in that year. And basically, if we look at these results in detail, you'll see that the fungicide response data do not sort by canopy height or canopy closure. So it really didn't matter how tall or short your soybean variety was or how bushy it was. It didn't matter in terms of response to spray volume. All that mattered in terms of response to spray volume was were the spray conditions, okay? And as long as you were within what are considered acceptable spray conditions between, you know, what's considered preferred delta T value, we never saw any penalty to applying with 10 gallons an acre versus 15 gallons an acre, okay? And so here are results for 2 sequential applications from 2022. Here are results for a single fungicide application from 2023, and now you can see that one study where we lost our yield data due to harvest problems. Here are results for 2 sequential applications from 2023. Sorry, this slide is erroneous. That's 2023. Very good. The last subject we're going to talk about is optimizing the number of fungicide applications. And what you'll find is, as we walk through this, is that first off, the soybean maturity you're working with within the range of soybean maturities that we deal with here in North Dakota matters, okay, as you think about 1 versus 2 applications. All right, and the likelihood that you're going to see a response to a second application increases with soybean maturity. Okay, basically, as soybean maturity increases, the bloom period lengthens, which means your window of susceptibility to white mold lengthens. Okay, very simple and it's very obvious. So basically, susceptibility to white mold increases with soybean maturity simply because the length of time that variety is going to be susceptible to white mold increases. So you get more opportunities to get the disease, if you will. All right, so we conducted research with a huge number of varieties, and this is replicated research where all these varieties are out in the same study, okay, and we tested the response to no fungicide versus single fungicide versus 2 sequential fungicide applications on each of these varieties with the droplet size calibrated relative to canopy closure at the time of application for each variety individually. Okay, so if variety X had an open canopy at a given date, that one, say it had 85% average canopy closure, that one got medium droplets. Okay, and if variety Y on that exact same date had a canopy that was already 95% average closed, that one got coarse droplets. So this is highly labor-intensive work, okay, because you had to go out with a different boom and a different walking pace based on the canopy closure for any given variety. Okay, these applications were typically always made 10 to 14 days apart. Okay, and with the number of days apart consistent within the study. Okay, and what you'll see here is that first off, you look at the white mold disease levels. They tend to increase with soybean maturity. Okay, the difference would be the oak site, where they had a couple years where the irrigation was not that intense, and so the overall pressure was lower. But all the other varieties, at least half the data were generated from Carrington, where we irrigated the same every year and got high pressure type environment every time. Now that's white mold percent of canopy, not incidence of plants. Okay, this is actually the percent of canopy. The incidence of plants would be quite a bit higher. All right, and so that's the percent of the canopy diseased or with poor pod fill because of a lesion that girdled the stem. Okay, and anyhow, what you'll see is that the yield response to the fungicide, you can see the yield response to the fungicide presented both as an average and as the results by individual variety. Those are the circles, okay, and the bars for the average. Okay, and so what you can see here is that the likelihood you're going to get a response to the second fungicide application increases with an economic response to the second fungicide application increases with soybean maturity. And the likelihood you're going to get an economic response to the fungicide increases with soybean maturity, period, whether it's 1 or 2 apps. Okay? But as you get to the longer maturity soybean varieties, you can see that you're making a really big gain by making 2 apps versus 1. That 1.0 to 1.3 maturity soybean, look at that. You only get 2.7 bushels by applying once, but you get 6.7 bushels on average by applying twice. So you're better off applying twice. Okay, with the 0.7 to 0.9 maturity varieties, you get 4.6 bushels by applying once on average, and 9.1 by applying twice. So this is a situation where the gain from a single application is 4.6, and then you go to another application, you gain another 4.5. I mean, it's not like those maturity 1 soybeans where you really need the 2 apps just to, make the fungicide really worthwhile, okay? But here you get a huge gain from a second app under high pressure, okay? And you can see that the gain from a second app declines as average gain from a second app declines as soybean maturity gets shorter, okay? But I will warn you, this was done with a 10 to 14 day interval between applications. I'll show you a little bit later from follow-up research that actually in these shorter maturity beans, it's very likely you're going to get a very strong response to a second application under high white mold pressure if you shorten up that interval, okay? And so so this understates the return to a second application in those shorter maturity beans. Okay, so first off, here are our results broken down by individual study and disease pressure. From those studies, as well as some other ones we've done over the years, with 1 application versus 2. Now, the previous testing was done always with 5.5 ounces of Endura, whether it was 1 app or 2. Now, this testing was done sometimes with 1 versus 2 applications of Endura at 5.5 ounces each time, or at 1 application at Topsin at 40, or generic at 40 fluid ounces. The label has recently changed for Topsin to allow a single application at 40 on soybeans, not 2, but 1. Okay, and or Topsin followed by Endura at 5.5 ounces, and you'll see the color code of the dot indicates which fungicide was applied. Okay, and anyhow, these are the double maturity beans up to a 0.0 maturity bean. Okay, and results from all of our studies, and what you'll see is the yield gain conferred by the fungicide relative to disease pressure in the non-treated soybeans, end of season disease pressure. And so what you're seeing is that the break even for a single fungicide application was 11% of the canopy disease. And for 2 sequential applications, 18% of the canopy disease at the end of the season. Obviously, you're going to have to make an educated assessment based on the susceptibility of the variety, the history of the field, and the white mold risk on whether or not you're going to hit this level of pressure if you do nothing. Okay, and that's what you got to do. But basically, if you were to do nothing and at the end of the season you had 11% of the canopy disease, you would have, on average, broken even by applying a fungicide that costs you $30 an acre. Okay, and you had $13 a bushel beans. Okay, and 2 sequential apps would have, the break even would have been 18% of the canopy diseased. Now, basically, you hit this in those short maturity beans only in really susceptible varieties under high pressure years, in my experience. All right, as you go to 0.1 to 0.3 maturity beans, notice the break even points drop. Okay, the bloom period is longer, which increases the yield potential and also increases the window of susceptibility. The break even for a single app is only 8% of the canopy disease. 2 apps, only 11% of the canopy diseased, end of the season. Okay, and again, this is based on a $30 an acre total application cost, product plus, that cost of putting it on. Okay, and based on a $13 bushel soybean price. Obviously, this break even is going to be even lower if you're putting on a cheaper fungicide. Okay, that's still as effective as 5.5 ounces of Endura or 40 fluid ounces of Topsin. In this case, these data are all for 5.5 ounces of Endura. In 0.4 to 0.6 maturity soybeans, now you have data where we applied either Endura at 5.5 ounces, Topsin at 40 fluid ounces, or Propulse at 6 fluid ounces. Now, in every one of these studies that I have, we had a non-treated control, the fungicide applied once versus fungicide applied twice. Okay, every one of these studies had all 3 of those treatments. The fungicides applied differed based on the color code you can see on the dots. On almost all the cases, it was Endura at 5.5 ounces, but you can see there's a handful of studies where we applied something else. But the results are consistent by fungicide. These are all effective fungicides against white mold. Okay, and so what you can see here is that your break-evens have now dropped a little bit more. You were down to 8% of the canopy disease for a single app and down to, the same as last group, but now notice the break-even for 2 apps has dropped. And notice that the consistency of the response to the fungicide is much better when you have 2 apps, okay, because that's giving you extended protection into the season, because 1 app does not protect you through does not protect you through the window of maximum susceptibility to white mold, especially because you have to remember that new growth is not protected. Okay, so the 0.7 to 0.9 maturity beans, you can see now the consistent response to the fungicide increases even more with 2 apps versus 1. Okay, you have a lot of failures when you only have 1 app, because frankly what's going on there is that you got your application on at R2, but you had lots of infections coming in at R3 or even early R4, and a lot of that's coming into new growth that wasn't protected, and so you needed that second app. Okay, and so notice that here the break even for a single application is all the way down to 4% of the canopy diseased. Okay, that's really low. Okay, but again, 2 apps gives you much better consistency control and is really needed if you have any level of disease pressure that would be, frankly noticeable. Okay, all right. So going on to 1.0 to 1.3 maturity beans. Now this is interesting. Disease pressure in these studies was generally a lot lower, okay, because again, the irrigation issues that I described earlier that just weren't irrigated as hard, okay, but what you can see is that the average response to the fungicide with that single app was actually fairly consistent. It was just a hair below the 2.3 bushels that we would have needed to break even with a $30 application cost and total application cost, product plus application, and a $13 bushel bean. Okay, in essence, it doesn't mean that the break even is really 29% of the canopy disease. What it means is that you just need a slightly cheaper fungicide if you think you're going to have really low pressure and only going to do 1 app. Okay, that's what that means. Okay, you need to get your costs down a little bit, or you have to have higher value beans. All right, and notice that the the break even for 2 apps is the same as it was with the 0.7 to 0.9s. Okay, and but basically a single fungicide application, just like we talked about earlier on these maturity 1 soybeans, is just not enough to carry the day. All right, and the window of susceptibility is too long. You really need 2 apps when you get to maturity 1 soybeans if you have any risk of white mold. All right, so the next thing that we need to discuss, though, is the interval between applications. Okay, that testing was done with a 10 to 14 day window between applications, which is the standard recommendation. But we tested whether that's actually optimal. And what we found is that in the shorter maturity beans, you actually should be shortening up that window. Now, this makes complete sense, because you remember that window of susceptibility is shorter on shorter maturity beans. So of course you got to shorten up the window, right? So on soybeans of 0.6 to 0.7 maturity, we optimized with a 7-day interval between sequential applications, which, by the way, is going to reduce those thresholds, okay? Because you can get better performance out of your fungicide. Okay, so basically your break-evens for 2 apps are even lower for those maturity soybeans than what I showed in the previous slides. Okay, if you get your application window down to 7 days. Now, on the soybeans of 0.9 maturity, we optimized with a 7 to 9 day interval. Again, shorter than what we tested in the previous slides. Okay, and in the soybeans of maturity 1 group soybeans, so 1.0 to 1.3 maturity is what we tested. We optimized with a 12 to 14 day interval, but I need to give you a caution. That data set is fairly weak for the maturity 1 soybeans. We are only able to test these in oaks alone, not oaks and Carrington, and we didn't have informative data from very many studies because of low disease pressure. And again, like I was talking about, just not irrigated as hard on a couple of years. Here are the results by soybean maturity. Okay, and what you'll see here is whether you look at the white mold severity or the soybean yield, the average data, or the scatter plot that shows the results by individual study, you see the exact same response. Okay, in this case, the brown means topsin on the scatter plot. The brown dot means a topsin at 40 fluid ounces applied once, or as the first app, followed by Endura at 5.5 ounces as the second app. Okay, and the blue means Endura applied once or twice at 5.5 ounces. Okay, but the results were consistent irrespective of the fungicide. Okay, but what you can see is that you're really optimizing the 7-day interval with both anywhere from a 0.6 to 0.9 maturity bean, but basically the difference between a 7 and a 9-day interval, a 10-day interval tightened. Okay, and as you went to the 0.9 bean. Okay, so the penalty applying with a 10-day interval was not as great. And in some cases, it was 10-day interval actually was better than 7 days on the 0.9. So basically, that's the basis of my recommendation. I said 7 to 9 days in my previous slide. That was a mistake. It was actually 7 to 10 days. Okay, so basically, that recommendation is based on these results. Okay, and this is testing conducted in Carrington and Oaks with very rigorous, deep data set for the 0.6 to 0.9 maturity beans. And you can see very clearly in the 0.6 to 0.7 maturity beans, you're optimizing the response to a second fungicide application by tightening that interval down to 7 days. And the 0.9 maturity beans, the difference between a 7 and 10-day interval is smaller. Okay, still 7 days on average is better, but and at least numerically, not statistically, but a 10-day interval was fairly close. Okay, as you got to the 1.0 to 1.3 maturity beans, most of this testing was done with 1.1 maturity beans. Okay. what you'll see is that we optimize with 12 to 14 day interval, but really the data set here is quite weak because the disease pressure was quite low. Okay, and usually as you get to these lower levels of disease pressure, you know, the response to a second application is more nuanced. It's a little bit smaller. Okay, so take the results for the maturity 1 beans with a grain of salt. Okay, the other results are very, very solid. Okay, and we did that testing, like I said, with either Endura applied once or twice sequentially at 5.5 ounces, or Topsin applied at 40 fluid ounces, followed by either once or followed by Endura at 5.5 ounces. Again, the label does not permit more than 40 fluid ounces at Topsin in a season. The label was recently changed to allow a single application at 40 fluid ounces. And what you can see, this is the combined analysis across studies where the white mold incidence was greater than 15%. Okay, so more than 15% of the plants with white mold. And what you can see is that we saw consistent results to the fungicide interval, irrespective of the fungicide program. Okay, in this case, you'll see that consistently under this high pressure environment, the Endura applied performed just a little bit better than the Topsin. Difference is not huge, but it's there and it's consistent. Okay, it might not be statistically significant, but you can see consistently the same response. Okay, where the Endura performs a bit better than the Topsin. It's close, but not identical. All right, now we did have some studies where the disease pressure was low. Okay, and this is the combined results where we had white mold incidence in the non-treated control at the end of the season of less than 15%. Okay, so less than 15% of the plants with white mold at the end of the season if you did nothing. Okay, what you can see is that in this situation under low pressure, okay, and what you're looking at is that a single application was sufficient, and this agrees with our data from the previous slides. Notice that the white mold percent of canopy was only 4% in the non-treated control. Okay, so you know, in no case did you see a threshold lower than 4%. Okay, and there was one group of maturities where it was 4%, but in no case lower. All right, and so basically, if you have very low white mold pressure, a single fungicide application is sufficient. And in this case, it looked like Topsin at 40 fluid ounces was equivalent to Endura at 5.5. Okay, so with that concludes what I had to share with you today. I will be posting to the NDSU Carrington website. Google NDSU Carrington plant pathology. Sometime here this winter, I will be posting a fungicide efficacy summary, basically efficacy results for all the major fungicides from our testing in Carrington. I hope to have that done by early February. Okay, and so check back and look at that website. You'll find an efficacy summary. One thing you need to be aware of is that our fungicide efficacy that we've observed in our trials has sharply increased since we started calibrating droplet size relative to canopy closure. And this is true for every single fungicide. Okay, the relative order of what fungicides perform best has not changed. Okay, so the best fungicides are the best fungicides whether applied with fine droplets to a closed canopy or coarse droplets to a closed canopy. The thing is that and the intermediate fungicides are still intermediate, but the thing is that all of the fungicides have improved in their performance significantly by adopting this procedure of calibrating droplet size relative to canopy closure, which is we now do in all of our efficacy testing. And the efficacy summary that I will be sharing and posting online, hopefully in end of January, but if not early February, will have results only from the efficacy testing study conducted once we started applying the results from our droplet size studies. Okay, so with that, thank you for your time. You can reach me by emailing me at michael.wunsch@ndsu.edu or by calling the office number at 701-652-2951. Again, efficacy data will be posted online. Google NDSU Carrington Plant Pathology, and you will find the page and you'll find that information posted there, starting in early February at the latest. Thank you very much, and I appreciate your time.